Before I forget, I also posted a homework 7. I don't remember if I told you about this or not. You don't have to do a homework 7. Just so make that clear right now. This was something that was going to be homework 7, but don't have time. So, but you might be interested in it, reading through it. For example, in the Introduction to Statistical Learning book, they have pictures that look like that. So they have a picture that says these are the classification boundaries for a two-dimensional classifier. So for each individual, we have two numbers, y1 and y2, PSA and age. And if y1 and y2 plot to the red region, we're going to predict as healthy. And if they plot to the blue region, we're going to predict as cancer. So that curve right there, how do you do that? How do you figure out the boundary is kind of interesting, I thought. And what we did in this assignment was simulated from a condition where this was really the boundary. In terms of the Bayes classifier, which is our optimal choice for classification if we can do it. So if we're going to do a simulation, we can just do it because we know the likelihood, we know we can pick the priors. So this is the picture of the Bayes classifier under a simulation model. You simulate some data and this is the truth. Now let's try some different classifiers. There's quadratic discriminant analysis, and the curve, the solid curve, is the Bayes classifier. That's the optimal boundary. You'll make the fewest mistakes on average if that's your boundary. QDA, quadratic discriminant analysis, its boundary, you have to watch where the blue and red trade-off is. But it's pretty close. So quadratic discriminant analysis allows for a curvy boundary like this one and did a pretty good job at capturing it. In fact, this model, the simulation model that we use here in this homework, was basically the quadratic model, a multivariate normal with different covariances in the two classes. We could do LDA in the next picture, and LDA in this case doesn't do as well because it can't curve. We're restricting, the L part of LDA means we're restricting the boundaries to be linear or in higher dimensions like planes. But in this case, the optimal is still that same curve. That's the Bayes boundary, and LDA did the best it could. So among all ways to just draw a line, that's the best one. But it made more errors than, say, the QDA model. If we look back at the QDA model, all the downward pointing triangles should be red. They should be classified as red because that was their true status. All the upward pointing triangles were really blues. So let's say it's PSA and age. All the upward triangles were prostate cancer. All the downward triangles were not. So for example, every time there was an upward triangle that fell into the red boundary would result in our model making an error. We would predict not cancer, and we're using the best model we can, but still it's going to make some mistakes possibly. So in this case, we would have made a mistake. And you can find others in the opposite direction. But this is like the best you can do with these data. QDA gets really close to the Bayes, but over here when we do linear, there's more mistakes. Over at the left, for example, here's a couple of downward pointing triangles that would have been correctly classified by QDA, but they were lost by LDA. So LDA is a higher level of assumption, I guess, on the data. That being said, it often does pretty well. we're not necessarily saying we really believe that there's a linear boundary, but in cases where maybe you have a smallish sample size, imposing something kind of a simple structure like a linear model works well. In omics data in particular, there was a paper in 2004, I think, in a big stat journal that said with high dimensional data like genomics data where you have thousands and thousands of features, it seems to be, based on simulation and theory, that the more complex models could often be outperformed or nearly equaled by simpler classifiers, like KNN is a simple classifier, LDA is a simple classifier. Support vector machines and random forests are not simple classifiers. And so the punchline was, with really high dimensional data, where the number of features is much bigger than the sample size, you don't have enough information really to fit something really complicated necessarily. So LDA does not do a great job here. It doesn't look like the best choice, but as a general tool, it does pretty well in practice. This was the same idea, but for the naive Bayes classifier. Naive Bayes says all the features are independent of each other. That covariance matrix is assumed to be diagonal. So instead of an ellipse for a multivariate normal, it's a spherical picture. It does okay, but I think QDA ended up doing the best. This was an ROC curve. Okay, so have a look at the homework if you would like to see how you would make that picture. Being able to make the picture, I found, kind of made me really understand what I was doing. It took a little thinking to actually make the picture. All right, let's go back to homework 6. 1A. Right, okay, so 1A, you're going to do K nearest neighbors. And part 1, take the training data, which is the first 225 samples. Take the training data and fit the KNN model for K equal to 1 to ... 10. So you have 10 fitted KNN models. Apply each one of them to the test data to get an accuracy. It's actually not the best way to do this. We would do better, I think, to do cross-validation for this. Because ideally, we would only use the test data once at the very end to get a single estimate of error. We're kind of using the test data here as for tuning the predictive model. What should we pick K to be? So if I would prefer to rewrite this part as do cross-validation, but you don't have to change what you've already done. It's fine. So to do the problem, you would take the training data and fit 1, 2, 3, 4 up to 10 KNN models for the different choices of K. Apply each of those to the 75 test samples and pick the value of K that gives you the smallest test accuracy. The highest test accuracy, the fewest proportion of mistakes whenever you applied it to the test data. Are there questions about that? Okay, and then part 3, there were questions here. So what you've done in part 1 and 2 is you've tuned the model. We said we want to use KNN, but we have to tune it, as in pick K. If we do Lasso, we have to pick that lambda thing. If we do LDA, we have to pick the threshold. Do we classify if p hat is bigger than 0.5 or what? So here we're tuning, and based on what should have been cross-validation, we have a choice of K. we're going to use k equal to 4, whatever it is, I don't remember. Before your findings can be turned into, say, a biomarker that somebody in a clinic would purchase and then use on people who walk in the door, what you would actually want to do is use all the training data to fit that final classifier. Think of the training data as what you're going to use to fit the model, and if you have to, evaluate its accuracy. Test data you're only going to use to evaluate the model. Having tuned the model already, we know what value of k we want. I'm not going to pick one of those models that we already fit. Each of them only used, well, let's see. Actually, you just go pick the one that you already fit. So for the different values of k, you fit those k and n models, get test accuracy, and then in part 3, if you stored all those models for k equal 1 to 10, then you have that model already fit. But if not, what you need is to fit the k and n model with all of the training data, all 225 samples, not the test data. So this is just the model on the training data for the value of k that you picked. And then apply that to the test data to get predictions and report a confusion matrix. So confusion matrix is a cross-tabulation of predictions and truth. It's interesting to know the overall misclassification rate. Overall, what proportion of times were your predictions wrong? But it's also interesting to know things like sensitivity and specificity, because those are more specific to what type of mistake did you make. Did I mistakenly say you had cancer when you didn't? Or did I mistakenly say you didn't have cancer when you did? It'd be nice to know like the accuracy for both of those. Because for example, if we never say cancer, and a cancer is rare, then if we always said no, we'd have overall a low error rate or a high accuracy. But if we looked at sensitivity and specificity separately, we'd see it was a worthless test. So when I say report the confusion matrix, what I would like you to do is maybe ideally, but I didn't specifically ask you this, but think about the overall classification error, sensitivity, and specificity. See if you can think of, what are those numbers? I didn't say it in the homework, so that's not going to be graded against you, but those would be 3 things to be able to write down, I think. Okay. So hopefully that answered the question that was on the board this morning. If not, feel free to holler back. All right, what I was going to do today otherwise was move on in the Introduction to Statistical Learning book to the chapter on model selection. Or we've been using the phrase variable selection. We have thousands of features, genes, SNPs, proteins, whatever, and we'd like to consider boiling that down to a smaller number of them, a subset of them. Maybe there's only 100 of my 15,000 genes that are sufficiently discriminatory. So imagine that we wanted to do, let's talk about doing prediction, as in continuous response variable that we want to predict a value for. Bone density or something. We would like to estimate bone density or in terms of a collection of input variables. So this could be gene 1's expression number and gene 2's and ... gene 30,000 thousands. In terms of doing this process of feature selection, coming from many down to a fewer number, a good starting point is a linear model. And we'll see why. There are some tools that are available to us that you're familiar with already, like stepwise additive regression and stepwise forward and backward additive stepwise stuff is a member of this class of things we're going to learn about. Let's see. Slide 4 says, kind of gives us options. If we have, say, 30,000 genes and we want to predict cancer, in terms of putting it into a biomarker form, it's not going to be practical to have every person who comes in the clinic actually construct a microarray for that person, maybe, or genotype their on a whole genotype SNP or something. That's too expensive. So can you say, here's a subset of those SNPs that we should genotype? Can you select out a subset that are sufficient for predicting? Subset selection is just that. You started with 30,000 SNPs, or whatever it is, and we're going to go out and find the best 100. At the end of that, then it is just 100 of the 30,000 that we started with. As opposed to the second option that's frequently used in statistical bioinformatics, called shrinkage. And what shrinkage does is, in terms of that linear model that we were starting with, that guy, think of response variable. You know, we're thinking cancer versus normal, so we could talk like a logistic model right here, or we could continue to talk about bone density or something. Some response is being related to a bunch of predictor variables, a bunch of genes or a bunch of SNPs, 30,000 of them. And in terms of a linear model, what we're saying is that there's a linear effect of each of these features on the response. If this was logistic regression, say, we'd be saying there was a linear trend to the log odds of cancer in this genes expression number, maybe. Feature selection, you could think of it like that. The subset selection, you could think of like, let's start with this model that has beta 1, beta 2, beta 30,000. And let's consider picking among those betas, a smaller number of them. Or picking from the x's, a smaller number of the x's. Of those that are already in the model, pick a subset of them. What shrinkage does is actually shrink the values of the betas, the estimated values of the betas, towards 0. So think of the model, you know, like the big betas would suggest, you know, big estimates of effects of these things. Forcing those things to go closer to 0 can, while it will bias the results, it brings with it often a large decrease in variance. Bias variance trade-off in a multivariate setting, you can theoretically show some benefits from shrinking. For example, there's a famous application of, just briefly, if you have multivariate normal data, so suppose X is a P by 1 vector, and this is multivariate normal with some mean vector mu, which is P by 1, and a variance covariance matrix sigma, which is P by P. The maximum likelihood estimator of mu, which we learn is, you know, like a great ideal to shoot for. There's different ways to estimate things, but MLEs are usually wonderful. Maximum likelihood estimator is what you would think it would be. It would just be the average of our n observed p-vectors. So the 5 biomarkers for me is x1, the 5 biomarkers for you is x2. Average those up, you have a 5-number average. That's the MLE, and it turns out that you can beat the MLE in terms of mean squared error. Mean squared error of your estimator, call it mu with a hat, is the expected value of mu hat minus mu squared. And it turns out that the MSE of a shrunken version of X bar. So what you do is, if I get this right, I'm just sorry, a X bar. Don't trust me on that. It's called a shrunken version. So you go component by component, and for each of them, you shrink the estimate there towards 0. So if it was a big positive number, it gets pulled in a little bit. If it was a big negative number, it gets pulled in a little bit. And you end up with an estimate, a vector estimate, that's less kind of noisy. The MSE for a shrunken version of a particular type, there was a famous statistician called Stein who came up with this. The MSE for that estimate is, I think, strictly less than that for the MLE. So it was kind of a paradoxical result. You can actually do better than the MLE in multivariate settings when you shrink things. I think we mentioned when we were talking next-gen sequencing that negative binomial model that we were talking about, and there were moderated test statistics that we talked about a little bit, where instead of estimating a standard deviation for each gene separately, they would assume some kind of smooth relationship among the variances, and try to pool the genes together to estimate a more stable version of the variances. So the T statistics in the early microarray days were so variable because these variances estimates were so variable. So then they started, quote, moderating the test statistics. It's the same idea, the shrinking of estimates, even though the individual choices of the estimates maybe make the most sense individually, overall you can often beat that choice by shrinking. So, I'm sure everybody is super enthused with that. Is that interesting? It's interesting to me, sorry. The shrinkage idea in the feature selection context is to go to that linear model that we started with, beta 0, beta 1, beta dot dot, or dot 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 beta 30,000, and shrink all those coefficients. So think of beta as a vector estimate, or beta hat as a vector estimate, just like X bar is a vector estimate for mu. 30,000 estimates. We're going to shrink the components of those 30,000 estimates towards all 0. Some of them will, we're going to shrink them. There's a couple of different ways to do shrinkage that we'll mention. A couple of different ways that are widely used. One of them is what we call Lasso. Lasso is a way to say, here's a model with a bunch of beta coefficients, and what I'm going to do to select variables is employ a kind of shrinkage. At the end of applying that, though, you now have a smaller number of variables that you're going to use in your model. Started with 30,000 genes, applied Lasso, tuned it, and maybe ended up with, I don't know, pick a number, 500 genes or something. You did feature selection, and you have the model that goes with it. Another option is to take your 30,000 features and use them to create new variables, a smaller number of new variables,
dimension reduction. So take it from 30,000 dimension down to 2 dimensions. What's the best way, in a linear sense, to take 30,000 features down to 2? You guys know the answer. Yeah. So you could do the principal component decomposition. You could do PCA, take your 30,000 genes down to, probably not 2, but so a smaller number. I don't know what it would be, but you might look at a scree plot or something and pick. Let's take the first 30 principal components. And then instead of that linear model we started with 30,000 betas, we'd have 500 betas. And chances are, by doing that, we would decrease substantially the mean squared error, or the misclassification rate, which is a combination of bias and variability. By throwing out irrelevant features and focusing on the ones that are going to be the most informative, you do better at what you wanted. So these are 3 options for doing the same thing. Subset selection, like stepwise additive modeling. You postulate a linear model and do backwards feature selection, where you consider, let's pick one out and see how it does. Now let's pick another one out and see how it does. And we'll stop after it seems like it's hurting too much. Or you can go the other way around. I'm going to assume you're somewhat familiar with that kind of thing. This set of slides spells it out if you'd like to read it. But the stepwise additive model selection, for example, where you start with a null model, i.e. a model that doesn't have any of your variables in it, no genes are in it yet. And then ideally, for every single possible size of, or for every, should you include one of your variables or 2 or ... all 30,000. For all possible sizes, fit all the models that you can that correspond to those. Go find the best 400 features, fit the model. Go find the best 401 features, fit the model. And pick the model that achieves the best accuracy. That's the ideal. What that usually ends up looking like in practice, because the number of possible models is enormous and impossible to do in practice, what often this looks like is the stepwise. Instead of considering all possible models, you consider adding one variable at a time. Which one variable would you add to the model in terms of fit quality? Which one achieves the best increment of fit quality? Then add that model, and then consider, now which one would I add next? And keep doing that until the model performance doesn't change much. That's the idea, and there's different flavors of it. I'm going to keep going. Because they spent a lot of time on those algorithms. I will just say there's relationships between, we have been talking about cross-validation as a kind of generic technique that we can use to train a model. What should K be? What should lambda be? How much shrinkage should we do? Stuff like that. Cross-validation. There are alternatives to doing cross-validation, namely statistics that quantify relative performance of models in a fair way. There are ways to quantify performance of models that are not fair, like resubstitution error. Fit the model on all your training data, predict your training data, how accurate were you? We know that's a biased estimate. It's overly optimistic. There are ways to get a properly not optimistic, or either way, not off, statistic based on how good, like the goodness of fit of your linear model. R squared, for example, if you fit a linear model with a bunch of covariates, R squared is a number between 0 and 1. Closer to 1 it is, the tighter the fit. It was a really good linear fit. The line in a multivariate sense went right through there, right through the scatter. R squared. R squared would always get better, though, if you kept adding variables. So if you only looked at R squared, it would just say use all your variables. You'll end up interpolating your data maybe, but you fit it perfectly in terms of R squared. So you don't usually look at R squared. There's an adjusted R squared, which balances that raw number with a penalty for including too many variables. We're saying we want to, if we can, throw some variables out. We'd like to pick a subset. So we would like to penalize ourselves if it keeps trying to say add more and more and more. That's the idea of adjusted R squared. That's the idea of what's called the Bayesian information criterion. And Mallow's CP, which is also called Akiyiki information criterion, AIC. So I'll leave you to enjoy those on your own time. But just to reiterate, cross-validation is what we're doing that. Those are options. But those are most appropriate when we have, they are assuming we have a model that's right. Assume that linear model is right. Then what's the quality of fit? What if the model's dead wrong somehow? Is R squared even meaningful? Cross-validation is I don't know, I guess I feel like I like it better because it is more generalizable, I guess. You can apply cross-validation to anything, and you didn't have to specify necessarily a linear model. So cross-validation, I would recommend as your go-to choice for doing classification. All right. Shrinkage, we'll do this just briefly. There's two main flavors of shrinkage. One of them is called ridge regression and the other is called Lasso. I'm going to emphasize Lasso. They're very similar. Sounds complicated, but it can be expressed in a fairly non-complicated way. If you're going to fit a linear regression model, the idea, just draw a picture real quick here. The idea, if we just had one continuous response variable and one continuous predictor variable, would be to observe some data and then find the line that does the best at going through the bulk of the data in some way. And we defined that criterion to mean minimize the square deviations, the sum of the square deviations between the points themselves and the thing you're fitting. In a simple case like this, it'd be what's the difference between truth for individual I and fitted value for individual I, which would be the value of the line at individual i's x value. What's that difference? How badly did we miss for that person? Square it, and then average those up. So the solution to linear regression is that, and this is saying that, just in math speak. So the residual sums of squares is add up all the truth minus the estimates. The model says that the mean equals beta 0 plus beta 1 x1 plus beta 2 x2 plus ... So fitted value compared to truth. Residuals, or think of these as residuals, square them, so now every error is positive, everybody contributes the same way if it's a mistake, and add them up. If you minimize that, if you pick among all the possible betas to minimize that, you get what you usually see in R if you do a linear regression model. Beta 0 hat is this, beta 1 hat is that. That will result in the usual regression model. So, shrinkage, what is called regularizes that residual sum of squares. So if we were just doing regression, we'd be picking the model that minimizes this RSS. The shrinkage idea is to regularize or penalize that objective function by how noisy the betas are, basically. How big are they in magnitude? Add up the squared betas. If they're all really small, there's not much of an effect that you would have estimated for these different betas, then that's going to be small. But if there are some, at least, that are really extreme betas, maybe due to a lot of variability for that variable, for example, let's shrink that down because it's going to penalize the RSS. We don't want to favor that model. We don't like models that have noisy betas. So shrinkage is to add a penalty. RSS plus some tuning parameter, lambda, times a penalty. Ridge regression uses this as the penalty, the sum of the squared betas. So there's a lambda tuning parameter. How much should we penalize? That's the idea of ridge regression. So here's a picture for a particular example where we have a model with income, limit, rating, and student. These 4 variables. And we're going to vary lambda. Increasing lambda will result in more and more penalty on erratic betas or anything being very far away from 0. So it's going to tend to shrink down the beta coefficients. These are the plots of the beta coefficients. Up here, the estimated, or the coefficient for the variable limit was up here around 420 something. And the coefficient for rating was there, and student, and so on. Applying this shrinkage, what happens is the betas change. They don't necessarily all go down as lambda went up. It's kind of interesting. The rating variable's coefficient actually went up some as lambda was going up, but lambda cares about the overall sum of those squared betas. So big picture, ridge regression is a method for shrinkage, which is a regularization or variable selection technique. What it is you change lambda and you force the betas to shrink down to 0. And the idea is that you hope that brings with it an increase in accuracy because you're decreasing variability. And just briefly, if you know what ridge regression is, you know what Lasso is very quickly, because what Lasso is what we had on the previous slide, RSS plus some tuning parameter times a penalty. It's just that the penalty is different for Lasso than it was for ridge regression. Instead of the sum of the squared betas, it's the sum of the absolute values of the betas. Don't have to know, the theory of why that is in order to enjoy the goodness of the Lasso. A good feature of the Lasso is that it turns out by using that form of the penalty, whereas ridge regression often results in no actual feature selection, it forces the betas to go close to 0, but they don't usually go to 0, which means you still have 30,000 genes in your model. The Lasso, it turns out, has the feature that it will actually shrink things to 0. So this picture, as you change lambda, you can see the beta coefficients, and some of them end up going to 0. They're gone. Those variables have been actually selected out of the model. That's why in the homework I asked you to do Lasso, not ridge regression. I think it's more appropriate to the context of bioinformatics. If you have thousands of features, you don't want a classifier that requires thousands of features for each individual. You would like to boil it down to a smaller number. Lasso does that, ridge regression doesn't. These slides may or may not be interesting to you. They're more from a theoretical perspective. All right, so All right, in the homework, which I was going to show you code for today, right? Let's show you code. Let's see. So that's Lasso. I'll show you code real quick here. And the last technique, we talked about doing subset selection, shrinkage, and dimension reduction, as in like principal components. Derive the first so many principal components and use those in your model instead of your 30,000 genes. The con data allow us to see some of this. So reading in the data, getting it set up. Clustering, differential expression, classification. Okay. So we've done this before. We're going to set aside some for training and the rest for testing. And I'm creating a data frame at the bottom there for each. Y-train DF is 54 by 2309. We have 2308 genes and 54 individuals. The first column of this is the group or the class membership variable. So to apply naive Bayes, we saw this, I think, already. We need the data frames, or it makes it easy to use them if we use a data frame. Then we can just say, name the column that contains my class membership variable, and use tilde dot to say, use all of the rest of the variables as covariates. I think we saw KNN. Lasso, let's use Lasso real quick. Probably going to have to install that. We're going to use the cv.glmnet function to perform cross-validation and tune the model. Okay, so let's see if this will work for us. Okay. So this right here, if you question mark cv.glmnet, is intended to, is saying, do Lasso. The alpha parameter is how you pick between ridge regression or Lasso. Look at the help file for cv.glmnet. You want to do Lasso, so say alpha equal to 1. What kind of model do you want to fit? This is a generalized linear model function, which means it can do linear regression, it can do logistic regression, it can do multinomial regression if you have more than 2 categories. So specify family equal multinomial, because we have 4 categories, I think. 4 or 5 categories. It's not binomial. The last argument here that I specified was, what do I want it to return to me? we're going to do a multinomial model. We haven't ever actually defined what that is, but it's basically an extended version of logistic regression to the case where you have more than two categories. What do you want back? Do you want like a log odds back, or do you want an odds, or do you want an estimate of P, the probability of being in a particular class? And what I asked for was which class was actually picked. So whatever you end up predicting for each of these models, give me a value of class. This function is going to tune the model for us. As soon as we say lasso, next question is, what value of lambda do you want? How much shrinkage do you want to do? That's where we use cross-validation. So cv.glmnet means we're going to do cross-validation to pick lambda. And it's going to thankfully do it for us behind the scenes. They have their own CV code behind the scenes. So when we do this, what we get back is cross-validation based misclassification rates as a function of lambda. They actually drew the picture in terms of log lambda for appearance purposes, but the optimal choice ends up being the biggest value of log lambda that achieves the smallest misclassification rate. In this case, you could have perfect classification according to cross-validation if you chose log lambda to be right there. So if we look at the names of CV Lasso, the lambda component is the collection of lambdas that it considered. So the software made an intelligent guess at a range of possible values for lambda to consider. How much shrinkage do you want to do? Here's a bunch of possible values. And for each one of those, it went and did cross-validation. Probably 5-fold cross-validation or 10-fold. I'd have to look at the help file. Inside CVM are the cross-validation based accuracies corresponding to the different lambdas. So if you plotted the log of that versus that, you should be able to reconstruct this picture. But the best choice, if you were to ask the picture, is this guy over here, lambda.min. So log of 0.047 is about -3, little behind -3. Okay. So you are okay, we're about out of time. We already talked about the feature selection thing. I can talk more about this tonight in the Q&A, but what we have done so far is cross-validation. We make this picture that tells us what value of lambda should we use. We've tuned the model. Once we've tuned the model, we want to fit the model and go apply it, like turn it into a classifier. So it turns out to do that, you have to use the glmnet function, as far as I can tell. And the glmnet function requires that you specify a variety of lambda possibilities. So what I did is say, here's a collection of possibilities. These are the ones you picked in cv.glmnet, and I passed those in as this argument. Otherwise, family is still multinomial. Type.multinomial, we're out of time. I'll have to comment on that in the Q&A. But we fit the model, and then we can go into that result and pick out the coefficients that correspond to, so basically the fitted values for the lambda that we want. So down, let's see, did we have a prediction? Yeah. There are coefficients. There are coefficients in this fitted object that you can go pick which model corresponds to the best lambda that we found. Then go get those coefficients. So whenever you do this code right here, let me go ahead and do all of this. And then we'll be done in 30 seconds. Okay, the CF Lasso that we just created contains the coefficients for all the 2,300 genes that we started with. We had 2,300 genes, features. We applied Lasso. We made a picture to watch as lambda increased. A lot of those, this is just a random collection of some of those 2,300, but you can see the coefficients going to 0. At the end of this, we picked a final value of lambda. It was the one that got the most accurate CV error. And inside this CF Lasso is the coefficients for the models for that corresponding model. Any genes that have a 0 coefficient are out of the model. They were selected out. So uh, 9,000. Well, there's multiple coefficients because of the way this model, there's a couple more comments to make, but the fact that there's very few non-zero elements in there means that we've shrunken the 2,300 down a lot. Feature selection. Okay, so that's how you can do Lasso. In the Q&A, I can talk about this part and anything else that you want me to talk about in a Q&A to help with this homework, say, or... All right, well then I'll stick to my plan. Okay, thanks.